This is a really complicated moving momentum problem. It's got a slope, so we've got trigonometry involved. We've got a little cart, so the mass is changing. We've got a jet that's coming down from a height, so we've got to account for Bernoulli going on here. There's a lot going on in this problem. So the water flows out of this reservoir under the influence of gravity, pours into this little tank car down here, which actually is rolling on a ramp. And we've got several questions. We know what the flow rate is, so what's the jet diameter at the exit from the reservoir at location 2 here? And the jet diameter when it reaches the car down here at location 3. We'll get those from Bernoulli's equation, because the velocity here will be determined by this height, 10 meters there. The velocity here will be higher, it will have increased and accelerated further as we get down to here, and mass will be conserved. This cable keeps things from moving, so it has to be enough to support the weight on the slope, plus enough to bring this water to a stop back here again in the car. And it says we can neglect any friction in the wheel and that the car is remaining stationary. And that right now it weighs 2,000 kilograms, so we can use that in our calculation. Finally, what if the car is not stationary but moving up the incline at a constant speed of 5 meters per second? So we would then have a box that's moving, and we've got to do a moving control volume for our force analysis. So first, the easy parts. Bernoulli from location 1 to 2. If we apply Bernoulli, we wind up with V2 equal to the square root of 2g delta H1 to 2, because the pressures are the same at the top surface and at the exit. And that height difference is 10 meters down to the exit from the reservoir. So 2 times g times 10 square root 14.01 meters per second. We were given that the flow rate is 0.2 cubic meters per second. So the area at 2, which is pi d2 squared over 4, must be equal to the flow rate at 2, that's q2 that we were given, divided by the velocity at 2, because q is equal to v times a. So we know the flow rate, we know the velocity, we can figure out the area, 0.01428 square meters, and back calculating to get the diameter, we wind up with d2 equal to 0.135 meters. So about 13.5 centimeters across. So fairly big. We do the same thing going from 1 to 3. This will be 20 instead of 10, and we get 19.81 meters per second, and d3 equal to 0.113, so about 11 centimeters. Still quite large. For question B, the little cart isn't moving, and we're interested in the sum of the forces in the x direction. And we've carefully chosen our x direction this way, so that we've got forces in the y direction like that, but we're not going to worry about them. We're only interested in the forces in the x direction. So the sum of all of the forces in the x direction must be equal to, from applying momentum, the momentum out, m dot u out, and that's going to be 0 because there's nothing coming out of the cart, minus m dot u in, the momentum coming into the cart. So the tension in the cable acts up the hill in the negative x direction. The mass of the cart acts down the hill in the positive x direction, and it's multiplied by the sine of 25 degrees to account for the fact of the angle. M dot u out, 0. M dot u in, density times flow rate, and we're given the flow rate, gives us m dot, and u in, the component in the x direction, is v3 times sine 25 degrees. Because as it comes down at v3 here, there's only some of that that is oriented in the x direction. The rest is oriented in the y direction. So we can rearrange that to get the tension equal to mass flow rate times V3 sine 25, the momentum contribution and the weight contribution. And if we plug all of that in with the right numbers, we wind up with just under 10,000 newtons. Now if we move to the moving situation, it's moving up the ramp. So although the contribution from the mass is going to be the same, there's going to be an increase for two reasons. One, more mass is coming into the control volume per unit time because it's moving up. So stuff is coming through here faster than it otherwise would. Likewise, the velocity relative to the control volume is bigger in the x direction because the control volume is moving this way. So there's the original velocity plus a component due to that increased motion of the control volume. So the velocity in is V3 sine 25, just like it was before, that component from here, plus 5 meters per second, the speed at which the control volume is moving that way. 13.37 meters per second. The mass flow coming in is the density times the velocity at which the jet is coming downwards plus the velocity at which the control volume is moving upwards. And that's 5, the 5 meters per second times sine of 25 degrees. All times A3, the cross-sectional area at location 3. So that's velocity, that's area, times density gives us a mass flow rate. Plugging those numbers in, 219.5 kilograms per second, just a little bit bigger than the approximately 200 kilograms per second that were coming in when it was stationary. So our tension now is mg sine 25 degrees, the same as it was up here before, plus an increased m dot in and u in, and the result we get is 11,226 newtons, about 10 or 12% higher than the original value because we're moving up the hill.